fundamental object, really, that we care about calculating, which is called the vacuum persistence. I forget, is that anyway, persistence amplitude. I start with the full interacting vacuum of this Hamiltonian. Okay? Now, if that was the Hamiltonian and this is the vacuum of the Hamiltonian, then I can let all the time in the world pass. I will obviously always stay in the vacuum. But instead, I have a perturbation, and that's this guy. Okay, so this is therefore the vacuum with J equals 0. And what I mean by this is taking into account that I'm kicking the system with this perturbation, okay, which is so again, if there was no J, I could drop this intermediate thing, because this is just the vacuum of this, and so it has, say, 0 energy. And I'll just get 1. But now I have this, and so this is a non-trivial thing. But this is what I mean by this expression. It's just this. And we can see, because we know quickly go to Feynman diagrams when we have a perturbation like this, or a perturbation like this, we can quickly see who this is. Okay? So contributions to this. Here's the typical contribution. So let me put it like this. This is x1, x2, x3, x4, x5, x6. And what I really mean here is integral d4 x2 j of x2. So this is the picture where, so let me write it as, let me just draw the notation, and let me just draw it like this and write an expression as that. So this is equal to the following: integral d4 x1, integral d4 x6, j x1, j x6, and then this where this is doesn't matter, x1, x2, x3, x4, x5, x6. Okay, so here's a very typical contribution to this in perturbation theory, where these blobs are just telling you that for every vertex, you actually have to integrate the x1, the endpoint, against this source. And so this is an order j to the 6th contribution to this thing. Okay. Obviously, there are a heck of a lot of terms. Formally, it contains all the j to the 6th terms, the j to the 7th terms, the j to the 8th term. This happens to be order lambda squared. There's order lambda cubed, order lambda, et cetera, et cetera, et cetera. So, but this is a typical contribution that's housed formally in this vacuum persistence average. So, more generally, let's see if I can just write the whole expression. Well, what you can see is happening is that any correlation function you could possibly imagine is hiding somewhere in the perturbative expansion of this. Okay? That's what it's saying. This is a house that contains every correlation function that the theory would have at loop level, tree level, you name it. And this is the fodder that ultimately gives us the S matrix. Okay, so instead of having to talk about all of these and all the diagrams that contribute to the n-point function or the n plus 7-point function and so on and so on, it's all just sitting in this one object. And in fact, we can write it like this. First, let me work non-perturbatively in lambda, but work perturbatively in J. And just write out the entire expansion in powers of J in one line. Okay? That is equal to the sum over the order in J that I want to work to. Formally work to any power of J I want. And then I'm going to have integral v4x1, v4xn. And then I'm ordered 5x1, 5xn. Okay. Just by following the just by following the so what I've used here is the general formula for perturbation theory, but where I'm treating, so this is where H is equal to H0, which is equal to pi squared plus grad phi squared plus, what did I write? Plus m squared. And H1 is equal to minus J. So the split of who I decide to perturb in is my choice. Right now, I'm writing something which is where the unperturbed Hamiltonian includes this interaction. And my perturbation is only in the source term. In that case, if I just use the general formula of perturbation theory, where this is the perturbation, then that's where these things are coming from. J, phi, J, time order. That comes from that master formula of perturbation theory. Whereas this thing is computed just non-perturbatively in lambda. Because I'm not perturbing in lambda. Now, if I focus on this guy and you tell me, please calculate it, then I would say, well, I'm a weak person, I can only calculate the perturbation theory. I might further expand this as a perturbation in lambda. But I haven't done it yet. I'm just showing that all of the endpoint functions, to any order in perturbation theory in lambda, or not perturbatively in lambda, all endpoint correlators are sitting inside this very compact looking object. By simply Taylor expand, this is another, well, sorry, let me not call it a Taylor expansion. Hold on. It'll turn out to be. Well, it clearly is. It clearly is, because look, I've written it out, and it's in powers of J, and we are perturbing in J, and so it is a Taylor expansion of this in powers of J. But the logic of how I got this formula was simply to do the general formula for perturbation theory, where this is the split between the unperturbed and the perturbed. That's all I did. So this is an example of what the mathematicians would call a generating functional. So the general idea of a generating function, which we are using, is suppose you want to prove, suppose you have a sequence of functions, fn of x, say, and you would like to prove something, some property of n equals 1 of the first of them, and the second of them, and the third of them. You would like to be proving some theorem about some property of f1 of x, f2 of x, f3. And you sense that there is some similarity in the proofs. And if you just had to sit and start writing the proof for the first case, second case, third, you would never end. So you'd like to just have a proof, a master proof that just covers the whole lot. Then one thing that aids in that is if you have some function g of two variables, say, where Taylor expanding in the second variable y is equal to sum over n, so Taylor expand in y. So suppose this is true. Suppose that's the Taylor expansion. Then, instead of proving something about f of 1, f of 2, f of 3, f of 4, if you can prove some property of g of x and y, it implies properties of all the fn, well, not fn. As long as the property does not intimately involve the y variable, then this g of x and y is just a convenient way of housing an infinite set of functions of x. And if you have enough insight into what the common features of this f, of all the different fnx's are, then there could be some manipulation of this function that automatically allows you to prove an infinite number of statements about all these infinite fn's. Okay? That's the idea. You might say, gosh, do we really have to do that? Can't we just say it at this level? And you'll see that some of the manipulations we do are truly subtle, that you could say it at this level, but it's just easier to just have this idea of a generating function. So this idea of a generating function or generating functional is extremely common in math, and we are adopting it. It could just seem like a very artificial trick, except that it also nicely latches on to this idea of guns and detectors that we are starting to think about anyway, and so the two go together so nicely that we must use it. And as you will see, it pays to think about this. Okay? So, so just to remind you, these are also just idealized sources. I just want to make one warning about thinking of these J's as sources, as physical gadgets that make particles and detect particles. They are the most idealized, they're the most ideal guns and detectors that you could have, and especially in one qualitative way. So first, are there any kinds of guns and detectors that would behave like this? Yeah. If you want this scalar particle, and you want a gun that produces it, well, if I carefully aim two fermions from time minus infinity to crash at some particular instant in time and space and make this particle, then this becomes a kind of an idealized J. Okay? But one of the things that the typical gun and detector in the lab, not for any deep reason, just as a practical thing, doesn't typically have is that if I have a J, and say I had a K, which could produce this particle, then of course, so here's space-time. J is non-zero in this region of space-time, K is non-zero in this region of space-time, and you're looking at their production of this scalar particle, then in fact you have to add the amplitudes. Okay? In other words, there's enough phase information. These are such idealized sources that they allow you to even have constructive interference with other sources. That's certainly true of particles like this. I could produce this particle through this kind of thing, or through some muon, and so on and so on. And we're used to, at the diagrammatic level, we would add amplitudes. We never do that. The main thing that is a little different with a standard source, again, it depends on the context. Sometimes you actually have some laser beam or something that's acting as your source. Then it might really have all this phase information. But often we have messier sources where if you have one source, you would just say, you don't go around saying it has an amplitude to produce this particle. You say it has a probability to produce this particle, and it doesn't interfere with any other probability. You just add probabilities. But that's because of the screwing. I mean, that's just some messy feature of the source that you can neglect the interference. Okay? But the most general idealized source is like this. That's the only thing that will perhaps push you in the wrong direction in some context if you think of it literally like some particular source that somebody hands you, is that often real sources lack the ability to interfere. But this can cope with that. It's just that this is the simplest diagrams will have this high idealization. But I think, therefore, it is very useful to start to think like a mathematician in this way, in what comes, but never give up thinking literally about what these sources are, because both are useful to make sense of what's going on. Okay, so in this sense, this is a generating functional for, so what does it manages to put its arms around? What are the infinite set of things that this one object contains? Well, obviously for these correlation functions. So that is often what is said when people say the generating functional, they mean the generating functional of all correlation functions. And if we further expand in powers of lambda, that is, whenever you see one of these, you say, I don't know what it is, I'm going to compute it to 10th order in lambda, then this is just going to turn into Feynman diagrams. Typical one looks like this. You're going to multiply by the j's and integrate. That's going to look like this. Define to be this. And so we also say that it is the generating functional for all the diagrams. Which diagrams? The diagrams contributing to the correlation functions. So one way to think pictorially is this object is simply your ability to look at every single Feynman diagram that you can possibly imagine where you haven't yet taken any S matrix limit. Instead, every line ends on a point, which I don't specify. I integrate over it with some weight given by j. Okay? But j is my choice. So in some sense, every possible finite diagram, meaning in the far future, it's still vacuum, in the far past, it's still vacuum. Unlike the S matrix element, where the particles go off into the future forever. This, as is necessary in what's to come, you'll see, this regulates the past and the future to be pure vacuum. Okay, we're always playing with the vacuum going to the vacuum. Yet, sitting inside those possibilities is everything else that we could ever want. Okay, okay, let me just make one more obvious statement when we're done. So this thing, we can define a second generating functional, we need to, is equal to e to the I. So the log, up to this factor of I, the log of this partition functional, or sorry, generating functional, it's also called, no, I'll say that at the right time. So this generating functional. There's this guy, okay, so this is the generating functional for all correlation functions, or all diagrams. And this is the generating functional for all connected diagrams. Okay, first, it's still true that all the diagrams appearing here, you would throw away the pure vacuum bubbles. Remember the vacuum bubbles, if you recall your field theory, the vacuum bubbles are the diagrams that you throw away. You throw them away and you have the I epsilon prescription, you end up with the correlators and the true vacuum. Okay. So we're already doing all diagrams except we're throwing away any purely vacuum bubble or vacuum factors. What do I mean by that? I mean that here is a diagram. Here's another diagram. The product of these two is a diagram. The product of these three terms is a diagram. We're never supposed to include this. Okay? En route to getting these correlation functions, I hope you have been taught that those are not there. They don't contribute. Okay? That is really secretly just setting the vacuum energy. You always get to choose what your zero of energy is. Keeping this is really just changing what you call the zero of vacuum. What is the origin of energy? And of course, we choose the energy of the vacuum to be zero. And that tells you this is still allowed. This is a diagram. The product of this and this is a diagram that contributes to this. And next time, so we'll run out of time, I'll show you that the log of this, they already know this, but the log of this is the generating functional of all diagrams which are actually connected. So you can see this is not connected to this. This is therefore not part of W, whereas this is part of W, and we'll just see why again next time. But this is the second generation.
the two most important generating functions we need. Okay, let's start.
Okay, let's stop there. Take over the next time. And by next time, we will just start path intervals.